Hi, in this video we are going to study the linearity property of the Fourier series representation. Now, let us assume that we have two signals, x1 of t and x2 of t, and they are periodic signals, are periodic with fundamental period, and their fundamental periods are equal, t0. Okay. Now, x1 of t and x2 of t therefore can be represented in terms of Fourier series expansions or representations, k from minus infinity to plus infinity, ak. Now, to show that these coefficients are the Fourier coefficients belonging to x1 of t, let us use the superscript 1 to denote this. E to j k omega 0 t, and x2 of t also has a Fourier series representation, say k from minus infinity to plus infinity, and let us use the superscript 2 to denote that the Fourier coefficients belong to x2, e to j k omega 0 t. Now, in both expressions, omega 0 is related to the fundamental period of the periodic signals by means of this relation, omega 0 equal to 2 pi over t0. Now, we have the following claim. We claim that the signal x of t equal to alpha 1 x1 of t plus alpha 2 x2 of t, alpha 1 and alpha 2 are arbitrary constants. They can be real or complex. The signal, which is in fact obtained by multiplying x1 of t with the constant alpha 1 and x2 of t with the constant alpha 2, and then we add the two expressions. The signal obtained by means of this operation has the Fourier series representation x of t equal to k from minus infinity to plus infinity, ak e to j k omega 0 t. Now, it is easy to see that when x1 and x2 are periodic with the same fundamental period, any such linear combination, in fact, this is the so-called linear combination in the context of vector spaces, but it is just a scalar multiplication by scalars and also the addition operation. it is clear that x of t is also periodic with the same fundamental period. Now the claim is the following, where the coefficients ak are obtained as follows. ak is equal to alpha 1 ak1 plus alpha 2 ak2. That means if we have the signal x of t defined as the linear combination of the signals x1 and x2 given by means of this expression, x of t is also periodic with the same period. This is quite easy to see, but the Fourier coefficients can be obtained in terms of the same linear combination operation applied to the coefficients. Now, we can prove this claim by just noting that, the proof of the claim is quite straightforward as follows. In fact, ak is equal to 1 over t0, and you integrate over any possible period. As long as you integrate over a period, you are okay. The integral x of t e to minus jk omega 0 t integrated with respect to t. Now here, it is clear that if we substitute x of t equal to alpha 1 x1 of t and alpha 2 x2 of t, then we can decompose this integral into two integrals. In fact, we are using the linearity of the integration operation. So this is equal to 1 over t0 from t0 to t0 plus capital T0. Then here we have alpha 1 x1 of t plus alpha 2 x2 of t e to minus jk omega 0 t integrated with respect to t. Okay. Now, it is clear that, as I have already mentioned, by using the linearity of the integration operation, we can express this integral as follows. It is 1 over t0. Alpha 1 is a constant, therefore it can be taken outside the integral. The integral from t0 to t0 plus capital T0 x1 of t e to minus jk omega 0 t integrated with respect to t plus 1 over t0. Alpha 2 can also be taken outside the integral from t0 to t0 plus capital T0 x2 of t e to minus jk omega 0 t integrated with respect to t. But it is clear that the first expression here is alpha 1 times ak1, the Fourier coefficients of the first signal x1 of t, and here we have alpha 2 times the Fourier coefficients of the second signal x2 of t. So this proves our claim. Now we can see an example of the implementation of this property. Now, before we continue with the example related to the linearity property, let us introduce a certain notation as follows. If we have a periodic signal x of t, remember it has a Fourier series representation with the Fourier coefficients or Fourier expansion coefficients, AKs. So this notation is just telling us that x of t is a periodic signal with a Fourier series representation where the coefficients are AKs. So with this notation, the linearity property becomes, with this notation, we can express linearity property as follows. X1 of t has the Fourier series coefficients AK1 and x2 of t has the Fourier series coefficients AK2. Maybe here we have to mention that x1 and x2 have the same fundamental period, capital T0. So x1 of t and x2 of t have these Fourier coefficients. Then alpha 1 x1 of t plus alpha 2 x2 of t will have the Fourier series coefficients alpha 1 a k1 plus alpha 2 a k2. So this new notation enables us to not to repeat the Fourier series, rather lengthy Fourier series expressions, but express the relationship between the signals and the Fourier coefficients by means of this new notation. Okay, now let us see the following example related to this property. Okay, let us consider the following pulse. P of t is as follows. It is non-zero over the interval from -1 to +1. So from -1 up to -1/2, it is equal to 1/2. Then between -1/2 and 1/2, it is equal to 1. And in the interval from +1/2 to 1, it is also equal to 1/2. So this point here is 1/2 and this is 1. So we have such a pulse. Okay, we obtain the periodic signal x of t as follows. We have the periodic extension of p of t with a period equal to t0, capital T0. So k from, or we can use the index m from minus infinity to plus infinity, p of t minus m t0. Now we can choose t0 to be greater than 2. You see that the duration of p of t is equal to 2. So if you use the fundamental period in the periodic extension of p of t as t0, satisfying this inequality, t0 greater than 2, then there will be no overlapping in the periodic repetition. Okay, the signal x of t is, of course, has now a Fourier series representation, and according to our notation, it will have the Fourier coefficients ak. Now, how can we obtain the Fourier coefficients? Of course, the straightforward approach is to write down the expression of ak in terms of the integral representation, integration over a period, and we can calculate the coefficients by means of that expression, or we can use linearity as follows. So our aim is now to calculate the coefficients. Now it is clear that p of t can be obtained by superposing the two pulses p1 of t and p2 of t, where p1 of t is the pulse. Okay, we look at p of t and choose p1 of t as the pulse which is equal to 1 over 2 from minus 1 to plus 1, and outside that interval it is equal to 0. And p2 of t is the pulse which is equal to, again, 1 over 2 over the interval from minus 1/2 to 1/2. So it's clear that p of t is the sum of p1 of t and p2 of t. Okay. Now, from p1 of t and p2 of t, we obtain the periodic signals as follows. x1 of t is the periodic extension of p1 of t, and from minus infinity to plus infinity, p1 of t minus mt0. And similarly, x2 of t is the periodic extension of p2 of t, from minus infinity to plus infinity, p2 of t minus m t0. So it is clear that x of t is just x1 of t plus x2 of t. Now here we remember the following. For the pulse, okay, let us call it P cap of t, which is equal to A. Okay, this point here is A on the vertical axis, and the duration of the pulse is t cap. So it is non-zero from minus t cap over 2 to t cap over 2. And from this P of t, we obtain a periodic extension of the pulse as follows: m from minus infinity to plus infinity, p cap of t minus m t0. Okay, and we remember the following. X cap of t has the Fourier coefficients. We have calculated this before. A t cap divided by t0, sinc of k t cap over t0. Okay, let us also remember what we mean by the sinc function, a t cap divided by t0. The sinc function is defined as sine k pi t cap over t0 divided by k pi t cap over t0. Now we are going to make use of this result to find the Fourier coefficients of x of t. So as we see, p1 of t and p2 of t are just p cap of t with a certain choice of a and the duration t cap. So just by inspection, we can write down the Fourier coefficients of x of t, ak, as follows. Now, x of t is the sum of x1 and x2. Therefore, we are going to find the sum of the Fourier series coefficients of x1 of t and x2 of t. Now, for x1 of t, the duration of the pulse is equal to 2 and the magnitude is 1 over 2. So it is 1 over 2 times 2 divided by t0 sinc k 2 over t0. And for x2 of t, we have p2 of t as the pulse, which is repeated periodically. The magnitude is again 1 over 2. Now the duration is equal to 1 divided by t0, and we have sinc k. The duration is 1 over t0. Okay, that's how we calculate the coefficients by using the linearity property of the Fourier series expansion. Okay, thanks for watching.